Okay, so let's assume that we've got a graph. And so I'm just going to draw the graph here and then, excuse me for a minute. I'm going to draw the graph here and then I'm going to try to draw the graph. And then we will look at how we would represent that in a typical way that it comes in. So I'll call this node 1, and this node 2, and this node 3. And I'll make sure there's a node 4, and 5, and 6. And then I'll have some edges here. I'll have one there, and one there, and one here, here, and here, and here. Okay, so we've got a bunch of nodes. We've got a bunch of edges. We can put some weights on them. So I'll just show you what we have so that if you go back and look at this later, you can see what they are. Although the examples I give you today, we're not actually going to be using the edge weights. So it shouldn't be a big deal, even if they're different. I'm just going to show you how they can be represented. Okay, so let's assume that that's our graph that we have. So we've got those nodes with those edges in there, and those are going to be the weights that we have that we're storing along the way. Okay, so when I write up code later on, when I write up an input file, this is the graph that I'm going to be working with. And so we might come back to this just so you can see it. Okay, and it's just for illustration purposes. And then later on, I'm going to add another edge. And I can't figure out how to change the pen color on here, but if I could, the other edge is going to be one like that, connecting 2 to 5. Okay, so that one will come later. Okay, so I'm going to switch over to looking at code now. But first of all, I'll write this graph as an input file similar to what you might have otherwise. So let me stop sharing this and start sharing this. And let me pull up the list of everyone. I don't know where the chat is. Hang on. Okay, so just so you know, I cannot, there's the chat. Okay. So just so everyone knows, I cannot exactly watch the chat as things are going on, but I'll try to keep an eye on it. Okay, so back to this. So I'm going to create the graph test data input file. So test.in. And this is old data that I had from a previous example. Okay, so I'm going to say that I've got something that's got 6 nodes. Those are the 6 nodes that I just listed there. And one that has 7 edges. And so the edges are going to go from 1 to 2 and have weight 4. And from 3 to 2 and have weight 5. And 1 to 3 with weight 7. And 5 to 4 with weight 6. And 3 to 6 with weight 1. And 4 to 3 with weight 3. And 5 to 6 with weight 9. Okay, so this is going to be the representation for that graph that I just showed you. And you'll typically see problems where when you have to read it in graph, it's something like this. You'll have something about the number of nodes and the number of edges. Those might be on the same line. Occasionally, you'll have something here in the middle that might actually give you like values that are at each node. So if there were a value per node, there would be like 6 numbers here. Okay, that give all the different values for the nodes, but then you would have something that gives the number of edges. And then for each edge, you would usually have the starting node and the ending node, and there might or might not be a weight. Okay, so something like this is how graphs are usually represented in input files. Okay, so I'm going to go ahead and create my file. First of all, I'm going to just show how we can read this thing in. So let me just include a bunch of stuff. need a vector. Eventually, I'm going to need a queue or a stack. That's when I get to doing breadth first and depth first search. We'll use queue or stack. So okay, so we're ready to write our program. So as far as reading the input, I'm going to first of all create a bunch of variables just so that I can read stuff in. So n will be the number of nodes I have, and k will be the number of edges, and I'll have some iterators like I and j, and some things like a, b, and w that are just used to read in data. So I'm just creating a bunch of integers right now. Probably the only ones that matter are I'm going to use n for the number of nodes and k for the number of edges. Okay, so I'll go ahead and I'll read in the number of nodes. And then if I wanted to, I could have some sort of statement like if there were values per node, I would do something like I equals, and I'm going to do one, by the way, I'm going to do all of this from 1 to n instead of from 0 to n minus 1, just because I think it's a little bit easier. But you can just subtract 1 off of all the node numbers and it works just the same. Okay, so I'm going to write this as if it's 1 to n. And so that means that everything I make will have to be size n plus 1. So I equals 1, I less than or equal to n, I plus plus. And I could, if I wanted to, I could have something in here that says, you know, read in values per node. Okay, but we didn't put that in the input file. There wasn't anything there, so there's nothing to do. Yes, question. That should certainly be a for loop. Thank you. I'm not off to a good start if I'm writing an if loop and an if loop. That would be nice. Okay, so yes, for loop. Thank you. Okay. Yeah, and unfortunately, I think I see someone put that in the chat, but I couldn't see it. Just your casual if loop. Yep. Nice. Okay. All right. And so the next thing that I would do is I would read in the number of edges. So read in my number of edges here, and then I'm going to loop through and read in each one of those edges all on its own. I equals 0, I less than k, I plus plus. And so I'll read in the starting node, the ending node, and the weight. Now, sometimes you'll have a graph where all of the edges are directed. So each edge is from A to B. And sometimes it's an undirected edge, so it's going to go both ways. So there are a few different ways that you can actually store your data. The two most common ones that are pretty much any time that you actually need to work with the graph and you're not just doing something like a minimum spanning tree, that you just need all the edges and you don't really care about the nodes. Most of the time when you do your graph representation, it's either going to be in a table or it's going to be in a list per node of what your neighbors are. Okay, so I'll switch to the table at the very end just so you can see it today. But for now, I'm going to create a struct so that you can kind of see what this is like. And you can make this as fancy as you want to. I'm going to do a pretty simple one. There's a lot of different variations that you could do on this, but this is just a simple way to keep track of it. So this struct, I'm going to call it a node. Okay, so I'll have nodes. And in the node, I will have a vector of the adjacent elements. Okay, so these are going to be all the things that are adjacent to me. So these are basically my edges. And I'll have a parallel array that'll be the weights of those edges. Okay. Yeah, question. Yeah, so this is going to be an adjacency list per node. Yep, this is the adjacency list approach, as opposed to the adjacency table. So I'll switch to a table at the very end, but I'll start out doing this with a list. And there might be something like might want something like a value per node. Okay, and for example, if we were reading in stuff here, this is where we would do something like we would see in, let's go ahead and create something here. Let's say we have a vector of nodes. v, and it's going to be of size n plus 1. Okay, and this is where we'd read in vi.value, something like that. Okay, so if we were reading in values, we'd have something like that in there, but we're not reading in values here. Okay, but here we read in an edge, and so what we're going to do with that edge then, for every node that we have, is we're going to stick that edge into A, and we're going to stick that edge into B. Okay, so we would say v sub A into its adjacency list, we're going to push back B. And then in parallel with that, we are going to push back the weight for that edge. Okay, so node A, or vertex A, however you want to think of it, is going to have an adjacency list, and it's going to say, I'm adjacent to B, and then whatever element there, it will have the weight. Now notice you better not sort your adjacency list, because that's going to get out of sync with the weights. If you need to do something like sort your edges, if you ever need to do that, you need to use a structure for the edge so that the result and the weight stick together. You could use pairs or something like that if you want to. Okay, but just be aware of that. And then we do the same thing. We do the same thing the other way around. So for B, we'd put A in its list. Okay, so this is going to create the adjacency list for the entire thing. And pretty much that's it. Now we've got our adjacency list. We've read in our graph, just like from the file that I had. Each one we read in the starting node, the ending node, and the weight. If this were a directed graph, we would skip these last two lines. So if it's a directed graph, you don't do those parts. You just read in the one direction and store it in the source node. Okay, any questions? So let me see. Why not use an unordered map to represent the graph? There are lots of ways you can represent the graph. Okay, I find this easy, but there are a bunch, including the table that we'll mention in a second. Yes, question. I find this easier to follow, but if you find it easier to use pairs, you can use pairs. It doesn't particularly matter. So the reason I like to do it this way is because I'm about to ignore the weights when I do breadth first and depth first search, and so I don't want to have to mess with always pulling out the first element of a pair. It's just easier to do it that way. Okay. Okay, so this shows you one way you could do it. Storing an adjacency list per node. Now, you don't actually have to, if you didn't want to, you don't actually have to create the node data structure. You might notice that the node data structure is really basic here. So I could have just made a vector of vectors for adjacency and a vector of vectors for weights and a vector of values. And that all of that would have worked just fine. Okay, so there's no particular reason that I had to use a structure other than I think it makes it a little bit easier to understand what's going on. And it's not going to be any less efficient to use a structure like this in this case. Okay, so let's go through and show you how to do a breadth first search example here. So breadth first search, if you remember, the idea of it is we're going to start at a node and we're going to look at everything adjacent to it, and then we're going to look at everything adjacent to it, you know, each of those and so on, and sort of work our way out. And breadth first search has the advantage of giving you a distance value for an undirected, or sorry, for an unweighted graph, at least undirected graph. It's going to give you a you can use it to calculate shortest path. Sorry, I think I messed up what I was saying, but hopefully you get the idea. What we'll do here for a breadth first search is I'm going to store in the value that I happen to nicely set up for myself earlier, this value element here. I'm going to use that to store the distance that something is away, just so I have it, just so that I can see what it is. And then I'll be able to output that at the end. And notice I'm going to ignore the weights. I might as well not have the weights here. I'm leaving it in here since the data file had it, but I'm not going to ignore it. So the distance is not based on the edge distance. It's just how many nodes away something is. Okay, so keep that in mind. This is not a weighted distance. So I'll start out by initializing everything. So I equals 1, I less than or equal to n, I plus plus, and say that v sub I dot value. Okay, so I'll start out saying everything is far away, and then I'll go ahead and I'll say I'm gonna start with my first node, with node number 1, and so I'll say that it's going to be at a distance 1 away. I could set it at a distance 0 if I wanted to. Would you rather see 0 or 1 for the initial node? 1. Okay, I got to vote for 1 here in the room, so 1 it is. Okay. So the first node is going to be at a distance 1, and we're going to keep a queue of ints, and this is going to be the set of things that we need to look at. This is the set of nodes that we're going to look at. So I'll just call my queue Q, very fancy, and I'll push the number 1. I'll push that first node in there. So right now our queue says I'm at the first node. That's the only thing in the queue. And then basically I'm going to continue. So while not queue.empty. So as long as the queue is not empty, I will keep doing stuff. Okay, and before I actually write this, I'll go ahead and I'll write my output here. In the very end, I'm going to go I equals 1, I less than or equal to n, I plus plus. And I'm going to output what those values are. So v sub I dot value. Okay, so I'm just going to output for each of the nodes how far away it is, what its distance value is that I compute in the breadth-first search. Okay, so I do this as long as the queue is not empty. So I'm going to go ahead. If you remember, I had A. I'm going to say A equals queue dot front. So I pull the thing off the front of the queue and pop that element off. Okay, wait, I see a chat question. You want v sub 1 dot value equals 1. Thank you. Yes, I do want v sub 1 dot value, not just v. V sub 1 dot value. Thank you. V sub 1 dot value is equal to 1. Makes sense? And actually, let me just stop this and make sure I don't have any other problems right now. So, okay, so that compiled and so you can see right now everything has distance -1 except the one that I set to 1. Okay, so stuff is working at the moment for what I had. Okay, so just a quick check, make sure I didn't have any other typos or problems so far. Okay, so we have our someone's in the waiting room. Sorry. Let me actually see if I can make Drew. Is Drew in here? Drew, I am going to make you co-host just so you can potentially admit people to from the waiting room if you happen to see. Okay. So we pull the first thing off of the queue, and this is the next node that we need to handle. And so what we're going to do in a breadth-first search is now we're going to look at all the adjacent nodes, and if they have not been visited yet, then we're going to go ahead and set them and stick them into the queue. Okay, so I'll say for I equals 0, I is less than, and so this is going to be v sub a dot adj. So I'm going to go through the entire adjacency list. Okay, however many elements are in there. And I'm going to pull off whatever the element is. So I will say, I guess I could make this B. So I'll go ahead and assign to B whatever the adjacent element is. So B is going to be v sub a dot adjacency sub I. Okay, you don't have to do that if you don't want to, but it saves some typing later. Okay, so B is going to be the other end of some edge of A. And so then I will check, I will say if v sub b dot value is greater than -1, in other words, if I've already seen it, then I'm just going to continue. Okay, so that would just exit me out of the loop. The other option I have that you might find easier to work with is instead of doing this, I'll just do this. You could do this either way, but I can say if it's still equal to -1, in other words, if I've never seen it before, then I need to process it. So what I will do in that case is I will say that vb.value, it's going to be one more away than the node I'm on right now. So wherever I am right now, it's going to be one more away. So that's going to be v sub a dot value plus 1. Okay, and then I need to put this in the queue. So I'm going to put v into my queue. Okay, and that's it. That's the breadth first search right there. Okay, is I go to a node, I pull it off of the queue, and I say I'm going to look around at all of the things I'm adjacent to. If that thing has already gotten a value, it means I've already seen it, so I can ignore it. I don't need to deal with it. But if it doesn't have a value yet, then I say, okay, it's one farther away than where I am right now. I go ahead and I set that, and then I put it in the queue so that when I come to that later on, I can then go around to its stuff. Does that make sense? Okay, so let's try this out. No typos. Okay, and so here's the results that I get. So I'm gonna, if you look at this, it's node 1 is 1 away, 2 and 3 are 2 away, 4 and 6 are 3 away, and 5 is 4 away. Okay, so I'm going to quickly switch back to the PowerPoint just so you can see it and verify that. Get that in your head for just a minute. Okay, so notice that this one right here, is 1 away, and that one was 2 away, and that one was 2 away, and this one was 3 away, this one was 3 away, and this one was 4 away. And we did not, this edge here was not there yet. Right? We did not put that in the test. Okay, and so if I did add that edge in, notice that node 5 down there should also be 3 away. Okay, so basically that worked. Breadth first search worked. It told us how many steps away we were. Again, we're not using the edge weights here. We're just using the number of steps. Okay, so back to our code here. If I wanted to, I can keep track of the time it takes and sort of the point at which I hit each of these nodes along the way. And this is sometimes useful to see just as an example. So I can create something here that's int time equals 0. And then every iteration of the loop, I say, I increment time. Actually, I'll do it right here. And then I'll output countered node okay. And so if I do the same thing here, okay, this will actually show you the order that you hit the nodes. So you hit nodes, the order of the nodes is 1, 2, 3, 6, 4, 5. Okay, so I'm going to stop the share and go back again. Remember that 1, 2, 3, 6, 4, 5, 1, 2, 3, 6, 4, 5. So going back here, notice I go 1, then 2, 3, then 6, 4, then 5. So it's a breadth first search. I do everything that's close to 1, and then one more away from that, and then one more away from that. Okay, so I'm gradually expanding out from where the original one was. Okay, so now let's see how this would look with a depth first search. So if we do a depth first search, what was this? graph. I'll change it to graph basics B. Okay, so what needs to change for a depth-first search? So it's actually very, very little that changes in the basic structure of what's here. So we still read everything in just like before. Okay, this is where we had our BFS. Now I'm going to change it to a DFS. And the only real change that I have to make is instead of a queue, I'm going to make a stack. And only because I want to show you how little you have to change, I'm going to leave the name as queue, even though it's weird to call a stack the name queue. Okay, so it's a stack, and instead of calling front on a stack, you call top on the stack, and that's it. Now I've got a depth-first search. Okay, that is the only difference between a breadth-first and a depth-first search, is are you using a queue or are you using a stack? And so now if I run this thing, okay, and I run a.out with test.in. Okay, notice the order that I'm going to hit the nodes here, 1, 3, 4, 5, 6, 2. Okay, so keep that in your mind, 1, 3, 4, 5, 6, 2, 1, 3, 4, 5, 6, 2. So when I switch back, I go 1, 3, 4, 5, 6. And then I've gone as deep as I can go in the graph. And so then I go back and I do number 2. Make sense? So the order that you hit them with a depth-first search is you basically plow forward as far as you can, and then you go back to hit the stuff that you didn't get before. With breadth-first search, you're gradually expanding out. But the only difference in terms of implementation is, did I use a stack or did I use a queue? That's it. Okay, now, one thing that you'll notice here, if you kind of remember the graph, if I go back to my results, if you look at these distances here, all of those distances came out identical to what we had with the breadth-first search. And you might be tempted to say, hey, depth-first search works. We have a graph that got the correct distance. You know, it didn't find it, you know, in the same order, but somehow it still ended up with the same values. And so this is where if we add that additional edge in, okay, so if I instead say I have an 8th edge, and that edge is from 2 to 5 with some weight doesn't really matter, so I'll just make it 1. If I add that edge in there, and I run this, I still get the same values. I'll scroll up here, 1, 2, 2, 3, 4, 3, 1, 2, 2, 3, 4, 3. I still get the same values that I got the last time, but that's incorrect. Okay, so notice, I'm going to stop share and go back. Notice that this says that node 5 is the distance 4 away. And now that I've added this edge in from 2 all the way down to 5, I can get there. 1 is 1, 2 is 2. So node 5 should only be 3 away. Okay, but because it did the depth-first search, it made it all the way down here to 5, and it didn't come back later and fix it and get the lesser value. So depth-first search is not a shortest path on an unweighted graph. Breadth-first is. If I go back and I run the breadth-first search on this same thing, so if you remember, breadth-first was the one that we called A, basic A.cpp. And I run that. Notice now I do in fact get that the distance of node 5 is 3. Okay, so it is the correct distance away. Okay, so that shows you how you would do these basic implementations of these structures, basic breadth-first search and so on. I want to show you the variation of this where you might use a table instead of a adjacency list, so that you can see what that might look like just as an alternative. Okay, I guess before I do that, does anyone have any questions? I'll bring up the chat window to see if anyone has one on the chat. say I'll bring up the chat. I'm not sure. No questions. Y'all are good. Okay, I don't see anything in the chat either. All right, so okay, so I'm going to start with my BreadthFirst search that I had last time, but I'm going to just show you how you can modify this so that instead of keeping adjacency lists, we keep an adjacency table. And the thing to keep in mind is adjacency tables are more efficient when you have a dense graph and you don't have any like weird cases like multiple edges and some other stuff like that. If you have a sparse graph where there's just a few edges compared to the maximum number possible, an adjacency list is usually better. But it's a little bit more cumbersome to code up and work with than a adjacency table or matrix is. Okay, so if we have an adjacency table, we don't need any additional structure, so we're going to get rid of this whole thing here. Okay, so we would still, read in stuff. We're no longer going to have a vector of nodes here. We would instead have a vector of a vector events. Okay, and these are going to be the edges. So this is going to be our edge table. So it's going to be an n+1 by n+1 table. And so I've already got a loop that's here from 1 to n. So each of these things, I would say v sub I equals, or v sub I can just call resize and make it also size n+1. And I can just go ahead and initialize the entire table to -1. Okay, so at this point, what I've done here is I've created a table. It's n+1 by n+1 so that I can index it 1 to n. So an n+1 by n+1 table, and I've initialized the whole table to -1. Good? Okay. And now that I've initialized it, as I read in, after I read in my edge, instead of all of this pushback stuff, I just say VAB equals W. So I just set the weight to be whatever that weight is. And likewise, I can say V from B to A equals W. Okay. Now, again, if it's a directed graph, you want to skip that line. Okay. So if it's only from A to B, but not from B to A, you skip that line in the graph. Okay. So one thing I don't have, since I don't have that structure that I had before, is I don't have a value here. So I need to actually create some additional vector that's going to let me store my values. So I will have a vector int value and make it size n+1 and initialize again that to -1. Okay, so that's going to be my values that I have along the way. And so in this case, I can set the value. I don't have to like use the value of 1 is equal to 1. All of this is the same. All of this is the same. Okay. Now, the loop that I have here is going to also be a little bit different. So I can't just go through my list of adjacent things. I'm going to have to look at every single one and say, is that thing that I'm going through here, is it possibly an adjacent node? So I'm going to create a loop, and I'm going to use B because B is going to be the other end. So I'm going to check, is there an edge from A to B for all the different B's? So B is going to be my destination. So I can just make that my loop. So for B equals 1, B is less than or equal to N, B++. So I go through all of them. I don't need to have that. And so what I will check here is I will say if, in this case, the value at B is -1, and I need to make sure that there actually is an edge from A to B. Okay, so I need to make sure that this vector up here that I set V, I need to make sure that it actually exists. So if V from A to B is greater than -1, or does not equal -1, and the value of b is equal to 1, and the value of b is equal to -1, then I want to do what I did before. So this becomes value of b equals value of a plus 1. Okay, and that should be it. I need to change the way I do this. Value of I is what's output. Okay, so again, the key ideas here are up here at the very beginning, I created an n by n table. So a vector of ints. I initialized it to have n+1 rows. And I need a semicolon. It has n+1 rows. And then for each one of those rows, I make it to have n+1 columns with everything initialized to -1. Yeah, question. Is that a question? Okay. And then as I read in all of my edges, I just go ahead and I set the elements of that table equal to the weight of that edge. Okay. That's set right there. And then everything else I have is pretty straightforward. Notice that I had to go through all the table. I had to go through all the edges. And so in a case like this, where I had 6 nodes, my table has 36 elements in it. Even though I only had like 7 or 8 edges, I'm looking to check for 36 different edges. So that's why this is good if you've got a dense graph where almost every edge is there. But if you have a really sparse graph with just a few edges, you're wasting a lot of stuff because this loop is going through a lot of values, and a lot of the values are going to be -1. So if I take this out and I run this, we'll see if it works. Okay, and that's the same stuff that I had before, same as the previous BreadthFirst Search. Okay, so that is what I had for today. I got through it slightly quicker than I wanted. Not than I wanted to. I'm happy to be done early, but faster than I thought I would. Does anyone have any questions? Yeah. Yeah. Show the code again. Is there a particular part of the code you wanted to see? Sure. Okay, so there's a question on the chat. Can you discuss the time complexity of the algorithms? So yeah, BreadthFirst Search and DepthFirst Search, each node is only going to be hit one time. Okay, it only gets basically enqueued or put into the stack one time. It's the first time it's encountered. Okay, so every node is going to be hit once. So order V, where V is the number of nodes. Every edge has to be visited. In fact, every edge is visited twice. But order, big O, it's the same. So it's going to be order V plus E. So every node once, every edge once. So they're order V plus E algorithms for DepthFirst and BreadthFirst Search. Now, if you have something that is using the table, then E is always going to basically be V squared, because you have to pretend that you have every single edge. Okay, and so something that is order V plus E is basically order V squared. Hopefully that makes sense. But I will say if the number of edges really is V squared, about V, on that same order, then usually the table is a little bit more efficient. It's just faster to index into it and so on. The tables don't work, and this, I feel like I'm repeating what I'm about to say in the video when I report it, hopefully tonight. But I might as well say it now. Tables don't work if you have multiple edges from one node to another, because each entry should just be one value. It would be a real pain to have a bunch of values per entry in the table. It doesn't work. You need to be able to identify if there's not an edge. So here I used -1, but what if you were allowed to have edges of negative weight or 0 weight and things like that? If you could have those, you need some way of designating this is not a valid edge. And so tables do break down in some cases, but when they do work, it's it's significantly more efficient to code and to work with. Did that answer the question on the chat? Yep, Reiki. Oh, so I think the question was, if I understood, why did I set this value to 1? I just said the first node is going to be distance 1. And then the next one would be like 1 away from that would be 2 and 3. If I'd wanted to, I could have just set this to be 0. And that would also, then the first one's at 0 and everything else is 1, 2, 3 away. It's just however you want to define it. Yeah. Yeah, so the question I think was, if you didn't actually care about the distance away and you just wanted to know, was it visited or not? Yeah, so you can actually keep a true false. You can just keep Booleans instead of a for the value, and you switch it to true every time you find it. And that'll just show you connected components. So when you do a connected component graph, that's exactly on an undirected graph or a directed graph, I guess. That's exactly what you do. Okay. Oh, wait, another question. V, yes, V plus E for both of them. Okay, so I will see you all in lab on Friday. We get out, what is it, 4 minutes early today. Okay, have a good rest of the week.